Well, I'd like to thank the organizer for the invitation to this exciting workshop. So today I'm going to talk to you about work on the fractional quantum anomalous Hall effect. So this effect belongs to the family of a quantum Hall effect. In the particular, right, it's a lattice analog of a fractional quantum Hall effect with a zero magnetic field. It's expected in the fractional chain sleeve. So this effect, right, zero magnetic field of fractional quantum Hall has been firmly established theoretically back to 2011 by these, these beautiful works. There's some kind of slightly details difference between all these different calculations, right? Either modeling or from these numerical calculation of the many body chain numbers, or from the model perspective, either from these spinful model or from spinless models, etc. But if we ignore all these details, right, there's one key elements is important to realize this effect, which is a flat chain band. So basically, that's the essence of this workshop, right? You need a flat band, you need strong correlations, right? You need a topology. So the question is then, how can we realize this effect? And what particular material system we need to work on? There have been a lot of proposals and on what the system you can look for. And so today, what I'm going to talk to is this twisted MOT2 bilayer, and that's what we discover this fractional quantum anomalous Hall effect. So there's two parts of my talk. So the first part is briefly mention our optical measurements of these chain-slated states using magnetic circuit diaprisms and using these optical spectroscopies. And the second part, I'm going to talk about the transport evidence of these results. In addition to these chain insulated states, we also observe something kind of interesting in the -1 half filling of the Mori unit cells. So let's get started. And the material system we work with is a transition metal dicotyledons, right, MOT2. If we look at the crystal structure of a monolayer TMDs, they have these hexagonal lattice structure, and each corner, right? One is Cockburn, the other is metal, so the inversion symmetry breaks already in the monolayer TMDs. And as my collaborator Di Xiao and Wang Yao pointed out, almost a decade ago, that this inversion symmetry breaking actually give rise to these important valley contrasting physical properties. So this includes these valley-dependent barrier curvatures, valley-dependent magnetic moment, and all these become important ingredients to realize these chain bands or topology in the systems. So our work is motivated by these two beautiful theory work. Right? This is from, the first one is from Alan and his collaborator at UT Austin. So this paper exactly pointed out that flat chain band actually can be realized in twisted MOT2. And the filling factor, for example, -1, you will see this quantum anomalous Hall effect. And the other one is from my collaborator, Wang Yao. So this paper is explaining actually where this topology coming from in this twisted MOT2. So let me just briefly discuss the physics behind the systems. So when you stack these two monolayer on top of each other in the rhombohedral stacking, means the top and bottom layer have same orientations. Then in a single unit cells, there's two energy degenerate point. So one is we call B, which is metal on top of Cockburn, and the other is the C, which is a Cockburn on top of metals. Then these two energy degenerate point, right? They form these honeycomb lattice structures. And the other interesting point is that for one sublattice C, right, it can be in one layer, and the other sublattice B in different layers. So then these sublattice pseudo-spin actually lock to the layer pseudo-spin, right? We have a top and bottom layers. This gives us an opportunity actually to control the Mori superlattice geometries. So for example, if you apply a vertical electric field across these bilayers, then you break the inversion symmetries, right? You immediately basically, they break the layer degeneracies between these two layers, then this honeycomb lattice will become into a triangle lattice. So these electric field tuned superlattice symmetry give us a knob to control the Hamiltonians, then the phase transition in the systems, and I will talk to you a little bit later. So The topology is coming from this Maury-induced Barry phase effect. So if we look at the equations of motion of electrons, right, there's two terms. So the first term is probably everyone familiar, is that in the second part you have these formula, which is cross product of this omega k is a Barry phase in the momentum space. So that's a pseudo magnetic field, right? That's how we, for example, give rise to this Valley Hall effect. But the second term, usually what you see is a V dot B, V cross B, which is a Lorentzian force, right? But actually in this case is R dot omega R. So R dot is just a velocity. Omega R actually is a Barry curvature in the real space. So in most crystals, right, it's a homogeneous crystal, then this Barry curvature in the real space actually vanishes. But that's the but however, in the Maury superlattice structure, right, this Barry curvature actually doesn't vanish. We can easily see from these layer pseudo-spin picture, right? We have, for example, we're starting from this point B, which is M on top of Cockburn, and you go to the sublattice C, you have a Cockburn atom on top of metals. Therefore, if you evolve from these points from B to the sublattice C, definitely, right, the layer pseudo-spin will evolve, okay? So this Maury atomic texture in the real space give rise to these layer pseudo-spin skyrmions, then that's directly give rise to this Barry curvature in the real space, and effectively we have this emergent magnetic field in the real space, and it's precision dependent. So these give rise the topological effect in the system. And our work also motivated by the other, the theory works and concern the FCI in such systems. One is from Liang Fu. They calculate the twisted bilayer WSE2 and pointed out that there's match angle 1.4 degree, give rise to these flat bands. And the other work is more relevant to our study is Kai Shun and Zheng Lin and the collaborator. They exactly calculated the twisted MOT2 and pointed out that at the match angle 1.4 degree, it's a spontaneous fractional chain laters. So what the spontaneous means is that there's a spontaneous time reversal symmetry breaking in the system. So I think, so we spend a lot of time actually studying these 1.4 degree. I think probably other group did as well. But turns out we cannot find FCI in these 1.4 degrees. So we basically search around, like shooting in the dark, and turns out we got some luck. So that's what I'm going to talk to you today. Right? Initially, what we found, there's a range of twist angle between 3.5 to 4 degree, give us the best results. And now we expand our study into different twist angles, and also there's a lot of study in the community, right? They point out that the range twist angle actually can be larger. So I will say the range of twist angle to observe all these phenomena is still undetermined. It depends on, but I feel like we make more and more devices and we'll understand more of the systems. So what I'm going to talk to you in the next few minutes is that first, I want to show you where the system actually have these ferromagnetic insulin states and the integer and the fractional Maury fillings. This is important because this gives rise to these spontaneous time reversal symmetry breaking. And the second part is then I will show you how we can determine these topological invariant, use optical spectroscopy technique of these ferromagnetic insulin states. First, I will show you how we measure these ferromagnetisms in these Maury systems. We use a magnetic circuit diagram. So in a simple way is we send in a laser and polarization modulated between left circular and also right circulars. Then what we do is we measure the reflectivity difference between these left and the right circular polarizations. This gives rise to these magnetic circular diagram we call MCDs. So if you're not familiar with this optical technique, you can think of an MCD as just a measurement of a Hawk conductivity at the optical frequencies. In our case, in particular, it's a measurement of the imaginary part of these AC conductivities. Okay, so this is the MCD signal intensity plot at the zero magnetic field. And the vertical axis, what I show you here is a filling factor, and the horizontal axis is electric field. And the twist angle of this twisted bilayer MOT2 is 3.9 degrees. And on the right-hand side, right, here's the structure of our samples. So we have bilayers and with dual gate. And what this dual gate does is give us control over carrier densities as well as electric field independently. That's what these two axes are. So what really stands out is that you can see in the phase space, right, in a large phase space, what I show you here at the whole doping site, we actually have a non-vanishing MCD signals. So this basically indicates we have a ferromagnetic phase space in terms of filling number and also electric field. So there's a lot of interesting features in this diagram. For example, right, wireless long tails like this. Okay, it goes into the electric field and the doping, etc. And those details are given, in our manuscript. I'm not going to focus on this. But what I'm going to show you is that by looking at these phase diagram, we already see there's two features. One is the fraction filling 2/3, the other is the filling integer filling -1. So here's this zooming of the ferromagnetic phase diagram I showed you, and we can focus on these integer fillings. Then we measure this MCD signal as function of the magnetic field sweeping back and forth. So clearly, right, you can see a very pronounced hysteresis loop. So this is just the hallmark of a ferromagnetism of the systems, and a similar thing can be done in all the filling factors. And the other interesting effect is that we perform temperature dependence, right, from the bottom to the top. We increase the temperature from 1.6 Kelvin all the way to 15 kelvins. So you can see the hysteresis nearly vanish at the 14 kelvins. This tells us that the Curie temperature of the system is about 14 kelvins. So at the first glance, you may thought that 14 Kelvin is a low temperature, but I will argue actually this is actually pretty high temperature. First of all, it's a two-dimensional system, right? We all know 2D magnetism, it has pretty low Curie temperature. But the second thing that's what's more important is that we're talking about this is a Morion magnetism. So we have 1 carriers per more unit cells. And the size of the unit cell is about 5 nanometers. So you can see that the spin density actually is extremely low. So at such low spin densities, we have about 14 Kelvin Curie temperature. So this already shows that something unusual happened in the system. Then the next is how can we determine the topology invariant of these ferromagnetic states? And there's two ways to do it, right? One is just do electrical transport, and you measure how conductivities. Then you can directly read out these chain numbers. So unfortunately, at that time, we were not able to do the transport measurements. So the second technique is to measure the fan diagrams of these incompressible states. So if these incompressible states, they can disperse as function magnetic field, then you can extract the chain numbers by using strata formula analysis. So basically provide the thermodynamic evidence of these chain-related states. So here's the two examples, right? The first one is from Xiaodong's paper, and they study the FCIs in these match angle twisted bilayer graphene. So you can see these FCI states. They show dispersion curve. Then at the at the low magnetic field, then the states will transition into a CW state. Okay, so you can see the CW state actually topological trivial because they not disperse as from your magnetic field. The other example I show you is from Ali study. They do STM measurements. They also measure the chain insulated states in match angle twisted graphene. So you see all the dispersion features, and they have different slopes, means different chain numbers. So we're gonna do this. We're gonna measure the dispersions of these states. But our technique is based on optical spectroscopies. So the reason we can do this is that twisted bilayer MOT2 is a direct bandgap semiconductor. So what I show you here is a collaboration with Elaine and Eli and the collaborators on nano up-pass measurements of a twisted MOT2 bilayer 4 degrees. So use these up-pass, you can directly see that the top of a valence band at the K values, okay? Then once we dope the system with potassium, then you can also see the conduction band appears. So basically you can determine this is really a direct bandgap with all the band edges happen at the K point. The other important feature is that the energy difference between the top of valence band to the gamma right, band is about 150 millieV. So these really large, actually, difference in terms of energies. So this direct band gap in bilayer give us opportunity actually to use spectroscopy, especially excitons, to study these topological properties. So what we use is called tryon sensing. And if you shine a light to a semiconductor, you're going to create a electron hole pair, which is an exciton. It's a neutral exciton. Then if we dope the system, then we're going to form a charged exciton, which is tryon. In this case, right, we hold dope it, we have a 1 electron and 2 holes. So here's an example of a photoluminescence spectra of a monolayer MOT2. On top, you will see a neutral exciton, and on the bottom, you see a charged exciton. So you can clearly see, right, the intensity are different, and they're also about 20 MeV shift in terms of energies. So we can measure these PL as as continuous function of a dopings. Okay, in these vertical axis, horizontal is the energies, and we see that at the charge neutral, you just see exciton. Then as you dope the system, you see tryons, either negatively charged or positive charge. What's important is you see the intensities and also energies. They evolve continuously as the doping density for these monolayers. Now the situation changed if we go to a twisted bilayer, and here's the data. I focus on the whole doping side. That's what shows the topological properties. Now you see that the PO intensity, right? It actually has these inflection point or these suppressed PO at these two feelings. One is the minus 2/3, the other is feeling factor -1. So the way we can understand these suppressed luminescence is that here I draw the band diagrams. I already consider the Mori mini band in the valence band for these twisted bilayers. So when there's the particular feeling factor, when there's a correlated insulin state, then the Fermi series open, right, it's gapped out. So when there's a gapped Fermi series, means that the number of free carriers actually will be reduced. Therefore, then the number of tryons also will be reduced because they need the free carriers, right, to form a tryon state. So when the tryon population is reduced, then we will see a suppressed luminescence in the spectroscopies. So whenever you see a suppressed tryon luminescence, basically shows that there's a formation of an incompressible state. Now we have an observable, right, to probe these states. Then what we do is that we measure the magnetic field dependent of these incompressible states. And I show you a 0 Tesla if we increasing the magnetic field. And clearly what you see, right, we can focus on these integer feelings. You can see the states actually, right, shifts as function of a magnetic field. So this already indicates the states are topological non-trivials. Now we can be a bit more quantitative. So what we can do is that we can do a spectral integrations of these spectra. So basically we get rid of these x-axis. Then we can just plot the integrated PO intensities versus the feeling numbers. You can see there's 2 dips, right? One is corresponding to the insulin state at the -1. The other is corresponding to the fractional feelings. Then we can plot these spectrally integrated PL as function of magnetic field. That's how we get these optical fan diagrams. And you can see 3 dispersion curves, right, clearly in a plot at the feeling factor -1, -2/3, and -3/5. And we can compare our data with strata formulas. The bottom is the lines is expected dispersions from these chain installed states from strata formulas, and these dots is the extracted depositions from all these spectral features. So they align quite well. And from this, right, we can basically infer the state at the feeling factor -1 is a quantum anomalous state. And the state at these fraction feelings, actually they're FCS states, okay? And the similar results also reported in MAC and the SANS work at the fraction feeling of -2/3. So what I show you here is basically, right, we have these, thermodynamic evidence of these FCI states, and shows the states can be extended into zero field and indicates where we have these fraction quantum anomalous effect. But we know that this is not a direct measurement, right? What we really like is to measure the Hawking activities. Okay, that's actually is a direct evidence of these fraction quantum anomalous effect. That's what I'm going to tell you in the rest of my talk. So I would like just show you the phase diagram first, and on this side, what I have is a longitudinal resistance, which is Rxx, as function of right electric field in the vertical axis, and the horizontal is the carrier densities or the filling number labeled on the top, and the right-hand side is the Hall resistance Rxy, and the device is 3.7 degree twist. So there's a lot of features, right, in these transport phase diagrams. So I want to just focus on a few things. The first, you see that the filling factor -1 within a large range of the electric field, right? The Rxx actually vanishes. So deep blue means vanishing Rxx. And correspondingly in the Rxy, you see that it's very large, right? Homogeneous signals. So this actually is the quantum anomalous state. Then we see the second suppressed Rxx pocket near the fraction filling -2/3, and correspondingly there's an enhanced Rxy. This is the fractional state -2/3. Then there's a sort of finite but a suppressed resistivity near a range of -1/2, but there's a very strong actually Rxy near the filling -1/2. So I'm going to tell you a bit more what we think what these states are. But you can also see that there's a suppressed Rxx between the filling -1 and -2/3. At the same time, Rxy also suppressed. So these phase corresponding to these ferromagnetic metals or anomalous Hall metal phase. And I'm not going to focus on this one in the rest of my talk. If you're interested, we can chat after my talk. Well, the other interesting feature is that if you apply, you see, once we apply this vertical, right, vertical is electric field, you'll see the states actually Rxx will dramatically increase of the large electric field, okay, for either -1 state, -2/3 state, or -1/2 state. So this tells us that by applying these vertical electric field, we introduce a topological phase transitions from these chain instance states into these topological trivial state. That's the superlight symmetry change was I talked to you at the beginning of my talk. Okay, so let's dive in. The first we just want to do fine diagram measurements just to confirm our optical measurements actually is correct. So what I show you is a fine diagram of these Rxy. The vertical axis is magnetic field, horizontal is the filling factor, and we can see there's three features, right? There's a broad feature, centered the filling factor -1. Then there's another two weak features. One is at -2/3, the other is -3/5. And this dashed line actually just expected dispersion curve from these strata formula analysis. And you can also see that by sweeping, basically by switching the magnetic field signs, this change state you see there also has these switch signs, right? So this is tell us really the state is coming from these magnetisms, but not from the quantum Hall effect. So this Venn diagram basically is consistent with the chain number, right, from these the optical measurements. Okay, so this is just a simple confirmation that the optical measurement and the transport measurement, they are consistent with each other. Then the next is we look at these individual filling factors. The first is at the -1 fillings. So we can measure these Rxy and Rxx by sweeping the magnetic field back and forth. You can see right the zero magnetic field, Rxy is quantized to h of e squared with a nearly vanishing Rxx. So this is just hallmark of quantum anomalous effect. We can repeat this measurement at three different twist angles from 3.5 degree to 3.9 degrees, and the results are more or less similar. So it shows that the effect actually quite robust across a range of twist angles. Right now, we can see all this effect all the way to 2.6 degrees. And the second feature I would like to emphasize is that the effect I talked to, the quantum anomalous effect, right? It's not new, right? We know that this has been demonstrated in many different systems. But I think what's exciting is the temperature is pretty high, right? So you can see that even at 8 Kelvin, this RXY is still nearly quantized. So we know that the quantum anomalous effect was initially demonstrated by Professor Qikun Xu, my friend Cui Zhu, back to 2013, right? So this year, 2023, marked the 10-year anniversary of these discoveries. So Yoshi wrote these beautiful reviews to celebrate these discoveries, but at the end, he highlighted the challenge of this effect, which is that the challenge to push the quantum anomalous effect to higher temperature, right? First to 4 Kelvin, then to room temperatures, right? To realize technology goals. So I was happy to say that at least we push the quantum anomalous effect above this challenge. At least we can realize above it 4 Kelvins. But I'm not sure how we can get to room temperature at this point. Okay, so the other interesting feature, right, is that then we can apply a vertical electric field to tune these topological phase transitions. So the red curve is the RXX, the blue curve is RXY, and the horizontal axis is electric field. You can see that when the electric field above 150 millivolt per nanometer, RXY quickly drops and RXX quickly rises into a insulin state. In this particular case, it's a ferromagnetic insulin state. And we can also perform temperature-dependent measurements, then extract the thermodynamic gap of these transitions. So in this curve, again, right, the vertical axis is energy gap in the unit of temperature. Horizontal is the electric field. You can see that as we increase electric field, the gap will close at this critical point and then reopen again. So these close and reopening of this gap basically tells us that this topological phase transition is a continuous phase transitions. Now I'm going to focus on these fraction fillings, right? Let's start with line traces of RXY and RXX as function filling factor. And right, we know RXY is inverse proportional to the chain number C. So as we tune the filling factor, you can clearly see that very quickly the RXY will increase to the value with 3/2, basically corresponding to the chain number minus 2/3, then drops. Okay, I'm going to come back to this point. RXY actually drops first as we keep Doppler system, then come up back again, reaches this value of 5/3, which corresponding to the filling factor 3/5. Then there's a little wiggles, then almost linearly increase as we reduce the filling factor. And across this number, which is the 2HV square at the filling number minus 1/2. Okay. So there's two states at the minus 2/3 and minus 3/5 is the fractional changeless states, right? Corresponding to this fractional quantum anomalous effect I was talking to you. And clearly, this linear dependence of RXY as function filling factor near the minus 1/2 filling, right, shows that the state itself actually is compressible. So it's different from these quantized state. And first, let's look at the filling factor minus 2/3. What I show you is just RXX and RXY as we sweeping the magnetic field back and forth. We can clearly see, right, RXY is quantized at the 3/2 as expected from this FCI state. And similar results can be done, right, in these minus 3/5 states as well. And you can see a beautiful quantization of the zero magnetic field at these expected numbers. So the quantization actually can be, for the 2/3 state, is as good as 99%. And for 3/5 state is about 97% quantizations. And an advantage of the system, as I already showed you, is that we can use electric field to tune these phase transitions, right, from these quantum anomalous effect into a tabular trivial effect. Again, right, the red curve is the RXX, and the blue is RXY, and the horizontal axis is electric field. So you can see that as we tune this electric field, for example, above about 20 millivolt per nanometer, RXY actually already start to drop. But above these 50 millivolt per nanometer, RXX quickly rise. So it indicates we transition into a insulin state. It could be just a generalized regular crystal state, and then drops again at a very large electric field. So it indicates we transition into a metallic state. So the exact nature of these states actually still remain to be explored, but at least tell us that this electric field is very useful now to control the topological phase transition of the systems. And so as these quantum anomalous if I talk to you, the filling effect -1, and the fractional quantum anomalous effect is also head temperature in the systems. So for example, right here, I show you the temperature dependence of these RxY and RxX measurements at these -2/3 FCI state. You can see that these quantization, right, is still pretty good actually at the 2 kelvins. So this actually is a remarkable temperature. Okay, if you're familiar with these fractional quantum Hall effect, and I get to talk to you at the end why I think it's remarkable at the 2 kelvins. So now we're gonna the last part